Um, let's do a computation of a trig function evaluated at an inverse trig function. And you know what? Let's even begin with like something kind of like a way of bypassing everything. We'll talk through everything, but let's use a computer to do some stuff. Let's start with intuition. What do you think inverse cosine and cosine of 17 pi over 1/3? What's the instinct for what that should be? All right, like trig functions should not do inverse trig functions, right? You really want that to be 17 pi over 1/3. The only reason that it isn't is because inverse trig functions have this weird step where you restrict domain. So just like how the square root of x squared isn't always x, it's plus or minus x, or absolute value of x. Same thing happens with inverse trig functions. Before we do this walk to computer, let's see what the answer ought to be using a machine. So let's pull up Desmos. Let's graph the inverse cosine of the cosine of x. There's the graph of the inverse cosine of the cosine of x. Is that just the same as the graph of y equals x? No, it is for a little bit, but then it starts like sawtoothing. So if I want to know what happens when I plug in 17 pi over 3, let's see what happens when I plug in x equal to 17 times pi over 3. 17 pi over 3 is like over here. I want the y value over that x value. So what does it look like inverse cosine of the cosine of 17 pi over 3 should be approximately by looking at this graph? About 1.7 and change. Oh, it's whatever that is. Oh yeah, about 1. I would round that to 1. All right, but they're like, okay, so you didn't see what I just wrote. By graphing, it's about 1. On the one hand, like, that's a reasonable way to think through things. On the other hand, if you like wrote that down as your supporting walk on a homework where I asked you to compute this and give an exact value, do you think I would be happy? No, for many reasons. One, it's not exact. Two, you haven't like done anything that demonstrates knowledge about what these functions are. So let's actually try to compute it. And let's compute it on the nose by thinking about what this is. Because you know. So what does inverse cosine of the cosine of 17 pi over 3 mean? It means find the simplest angle whose cosine is the same as the cosine of 17 pi over 1. That's fundamentally what this thing is asking us to do. So let's try to simplify that angle to give something else that gives the same value for cosine. And let's start by thinking about extra 2 pi's. Are there any extra 2 pi's in that number that we can get rid of? Is that like an angle that's bigger than 2 pi? Yeah, so we should throw out some extra fall revolutions. Let's just figure out how many there are by doing some long division. So let's start with this. What happens how many times does 3 go into 17? With the remainder of? The reason I asked instead of doing it was because in the earlier section I screwed up the remainder. And the other section was quiet enough that they didn't want to correct me, and so I just did everything wrong until almost the last step. It was really annoying. So I just asked you this time. All right, so that means that 17 pi over 3 is the same thing as 5 pi plus 2 over 3 pi. So far, so good? All right, so we can now throw out the excess 2 pi's. Let's throw out the excess 2 pi's and draw a picture of this. That 5 pi has 2 pi's in it. Has two 2 pi's in it. Let's throw out those two 2 pi's. That'll leave me with pi plus 2 pi over 3. And maybe I'll like combine that back together to be 5 pi over 3. And let's draw a picture. That's embarrassing. I don't know when I've last gotten a call from someone I actually want to talk to. This was spam. All right, an angle of 5 pi over 3. What quadrant does 5 pi over 3 live in? I hear a call for the second. Let's get a show of hands. Quadrant 1? Quadrant 2? Quadrant 3? Quadrant 4? I think it should be quadrant 4, right? Oh. Right. There's 1 pi over 3, 2 pi over 3, 3 pi over 3, 4 pi over 3, 5 pi over 3. So what quadrant is it in? Quadrant 4. Okay, good. So, let's remind ourselves what the range of inverse cosine is. What's the range of inverse cosine? That's the domain. Or the range of just cosine. So, the way to remember what the range of inverse cosine is. Inverse cosine of a number is supposed to be the simplest angle that recovers that x value, because cosine is the x value. So it looks like you can plug in, let's start at 1. What's the simplest angle whose cosine is 1? Zero? And it doesn't matter radians or degrees, but radians. Then as the x value starts going down from 1, it looks like the angles start doing this. Those are the simplest angles with that as inverse cosine. It continues tracing down. I think it traces out these 2 quadrants. What 2 quadrants did I just trace out? The first 2, quadrant 1 and quadrant 2. So that picture is the range of cosine inverse. Is this angle, 5 pi over 3, in the correct range? No. How would I get it into the correct range while preserving the x value? Yeah, flip it over the horizontal axis. So does it sit in the correct quadrant? No. Since it doesn't, let's flip it over the x-axis, the horizontal axis. And so I guess that means we need to describe this angle. What does flipping an angle over the x-axis do to that angle? And it like sticks an extra negative sign in front of that, right? When you reflect over the x-axis, you replace theta by minus theta, which we used earlier going the other way to figure out what theta replaced by negative theta does to trig functions. Let's just add this also. If you reflect over the y-axis, what does that do to an angle? You replace this angle by that angle. What does that do to the angle? Makes the x negative. What does it do to theta? Well, like, those 2 angles are the same, right? Yeah. But you usually don't measure angles starting at the negative x-axis. How would you describe this? pi minus the angle. That's not relevant to this problem, but it's a thing that you need to remember when you need to reflect over the y-axis. So, the simpler angle I get is negative 5 pi over 3. It's simpler because it at least gets me into the correct quadrant. So negative 5 pi over 3 is now in the correct quadrant. But is negative 5 pi over 3 literally between 0 and pi? No, it's negative. So this is an angle which gets me to the right place, gets me to the right coordinate that I want to land on. But it's not in the right range. Let's start adding some 2 pi's. Cosine doesn't care about 2 pi's. So let's add 2 pi to that and see what we get. What is negative 5 pi over 3 plus 2 pi? Let's add these like we would add fractions. We need a common denominator. What's the common denominator? So I'll leave the negative 5 pi over 3 alone for now. 2 pi is going to become something divided by 3. What's the numerator? All right, so it looks like I just need to know what 6 minus 5 is. Pi over 3, is that now between 0 and pi? Cool. So here's what we've done. We found an angle which lives between 0 and pi and has the same cosine as the angle we will get. That's what the inverse cosine of the cosine of the number is. And now, let's just think through if this agrees with the decimal approximation we got. Is pi over 3 pretty close to 1? Yeah, because pi is like about 3. It's a little bit bigger than 3, so pi over 3 should be a little bit bigger than 1. We can also resort to a computer. And so that gave me 1.047. That agree? Groovy. How do people feel about this type of example? Cool. So here's what I will suggest people do between now and the next time we meet. There are some other problems that I'll have you do as practice problems, but there's a collection of 4. Take some time on your own. I will expect at the start of class on Wednesday, not tomorrow, because this class doesn't meet tomorrow, to have some questions maybe about that. Or maybe even just to have some statement, like what are these things equal to? Maybe I'll do like a pop quiz. It's been a while since I've done a pop quiz. Still counts as a pop quiz because I didn't say I'll definitely do it. Nice. Cool. So, let's shift gears a little bit. We talked about inverse sine and inverse cosine. Are sine and cosine the only 2 trig functions? They're really like 4 more. There's tangent, cotangent, secant, cosecant. Secant, cosecant, and cotangent, those are just like reciprocals of the other 3. So I'll settle for figuring out how to undo tangent, and then we'll do something with it. So it's the same game as we did for sine and cosine to figure out what the inverse tangent should mean. And to do that, let's start with a graph. So, how many people remember what the graph of tangent looks like? Just graph it by memory, yeah. Well, let's try to graph it. Let's graph it by thinking about the units on it. Start at an angle of 0. So remember, tangent is like the slope of the line from the origin to that point. What's the slope of that line? So what's the tangent of 0? So if I want to graph tangent, tangent of 0 is 0. And maybe we'll draw one actual angle there. So let's see. As you start rotating up, as the angle becomes positive, what can you tell me about the slope of this line? Does it become positive or become negative? becomes positive. So the tangent will increase. It'll become positive. And let's go up to pi over 4. What's the tangent of pi over 4? 1. Because tangent is sine over cosine. What's the sine of pi over 4? Cosine is tangent is sine over cosine. So it'll and then the angle will keep increasing. At some point I just get a vertical line, right? So these slopes are getting like really, really, really big. What angle corresponds to this vertical line? Pi over 2. So the slope becomes like infinite close to pi over 2. It looks like there's a vertical asymptote. So this keeps on going. There's a vertical asymptote at x equals pi over 2. Let's also go negative. So if I take this angle and I rotate down a little bit, what can you tell me about tangent? Becomes negative. And so it'll become negative. In fact, let's do this. Tangent, even, odd, neither, or both. If you're a call for odd, if you're a call for neither. Let's remember which by like thinking about sine and cosine. So check for even or odd, plug in a negative for x. Tangent is sine divided by cosine. Is sine even or odd, or neither or both? So sine is the y value. So let's start at 0 radians and rotate positively or negatively. How do the y values compare for these lines? They're opposites of each other. So is sine even or odd? Sine of negative a number is negative sine of that number. How about cosine? So start at an angle of 0 radians and start rotating up and rotating down. How do the x values compare? They're the exact same. So what's cosine of negative x? You answered maybe the question I should have asked instead of the question I did ask. Cosine of negative x is cosine of x because cosine is even. Nice. So negative sine x over cosine x, what does that simplify to? Negative tangent. So now I'll ask the same question again. Is tangent even, odd, neither, or both? Odd. So that means I don't actually have to start graphing what happens for negative values. I know what happens for negative values. The exact same thing as happens for positive values, but negative. So there's a vertical asymptote here at negative pi over 2. And I guess that agrees. Right? If you start rotating down, the slopes become negative, and they get really big and really negative. Let's see what happens in the next quadrant. So there's the vertical asymptote here. If I rotate just a little bit past, what sort of slope is that? Negative and really, really big. And like any trig function, it's periodic. Nice. So there's the graph of tangent. Let's ask some questions about it. Is this function 1-to-1? Let's start with that. Is that function 1-to-1? Let's see, show of hands. There are going to be 3 options. Yes, no, and I don't remember what 1-to-1 means. It is 1-to-1. It is not 1-to-1. I don't remember what 1-to-1 means. Cool. So, a function is 1-to-1 if different inputs always go to different outputs. So like x squared is like 2-to-1 because like 2 and negative 2 both go to 1. 2 inputs go to the same output. The function is 1-to-1 if that never happens. Also known as, so you can check it graphically by the horizontal line test. How do people feel about the horizontal line test? That more memorable in terms of knowing what it means? So let's ask this question. Does that graph pass the horizontal line test? Folks vote yes. Folks vote fails the horizontal line test. I think that those who said it passes have just forgotten which option passing means. So a function passes the horizontal line test and crosses every horizontal line at most points. So let's draw a horizontal line. Maybe that one. How many times does tangent cross that green horizontal line? How about infinity? More than once. Does this pass the horizontal line test? Is it 1-to-1? So, does this function even have an inverse function to talk about? So it's weird to talk about inverse trig functions. You have to figure out what they really mean. But just like it's really useful to have the square root function, even though you can't really involve the squaring function, we'll still want to do something. So is it 1-to-1? No. So here's what we'll do. We'll try to come up with a restriction of the domain, which is as simple as possible, and so that tangent is 1-to-1 on that restricted domain. So what do? We'll start at the origin. I'm going to try to highlight as much of the graph as I can while still having it be 1-to-1. So let's start at x equals 0. How far to the right can I go before something bad happens? Pi over 4 is, did you say pi over 4? Let's go up to pi over 4. Pi over 4 gets me there. Could I keep going? Yeah. Pi over 2, that's where the vertical asymptote is. And notice, I could go past that vertical asymptote and get down here and it would still be 1-to-1. But I think that would be more complicated than necessary. How far left can I go from the origin and still have it be 1-to-1? Negative pi over 2. So if you want to only see that blue piece of the graph, is that 1-to-1? It passes the horizontal line test because I'm ignoring everything else. All right. Since that blue thing is 1-to-1, it has an inverse function. The arctangent function, noted arctangent or inverse tangent, or depending on what computer system you're using, maybe it's written down as a tan of x, is the inverse to tangent of x after you restrict the domain to negative pi over 2 to pi over 2. And maybe just for emphasis, the way I've written that, I am excluding endpoints. Why should I exclude those endpoints? Yeah, they're not even on the graph. They're a vertical asymptotes there. All right, so I'm going to take that blue piece of inverse tangent and invert it. If you know what the graph of a function looks like, then how do you get the graph of the inverse function? Switch the x and y coordinates. I have some x and y coordinates highlighted there. There's this one at 0, 0. What happens to 0, 0 when you switch the x and y coordinates? Yeah, it's still 0, 0. What happens to pi over 4, 1 when you switch the x and y coordinates? Becomes 1 pi over 4. This vertical asymptote says something like pi over 2, infinity, whatever that means, is on the graph. So when you switch the x and y coordinates, that would be like infinity, pi over 4 is on the graph. So there's a horizontal asymptote. At what y value? What's the y value of this horizontal asymptote? It should be like the same as the vertical asymptote. What was the x-coordinate of the vertical asymptote? Was I saying pi over 4 a bunch of times when I should have been saying pi over 2? Probably. That sounds like me. Nice. So, and then the same thing but negative. Cool. That feel pretty all right? So there's the graph of inverse tangent. Let's read some things off. Oh, this is the bundles. Even or odd or neither or both. Odd. If I want to pin down the origin, flip it 180, still the same graph? That's how to check for odd. So it's odd. What's the domain of that function? Infinite, but like more specific, because like 0 to infinity is infinite too.
Negative infinity.
Well, all the real numbers, negative infinity to infinity. What is its range? Yeah.
Negative pi over 2 excluded to pi over 2.
Negative pi over 2 excluded to pi over 2 also excluded.
Awesome. Cool. Let's just compare and contrast that with inverse sine and inverse cosine. What's the range of inverse sine?
Including or excluding? Including. And let's just draw a quick picture to remember why.
Maybe I'll draw 2 different pictures to remember why.
So let's start with the graph of sine, which is something that you definitely should have internalized soon.
And let's draw as much of it as we can while still having it be 1-to-1.
You can start at 0, go forward up to the top of that peak, but then it'll turn around and start not being 1-to-1.
And you can also go backwards to the previous. There's the bit you have to undo to get inverse sine. That peaks at pi over 2. That's why that pi over 2 is there. That value is at pi over negative pi over 2. That's why negative pi over 2 is there. What about the domain of inverse sine?
Maybe I'll draw like one more, like a unit circle picture. So there's the range of sine inverse,
Negative pi over 2 to pi over 2.
Same question for inverse cosine. What's the range of inverse cosine? 0 to pi, including. And I think that wants yet another picture. There's the range of cosine inverse. What's the domain of inverse cosine?
Also negative 1-to-1. The reason for that is, if I were to ask you, what's the inverse cosine of 140°, you would say, well, that would have to be an angle whose cosine is 140°. Cosine is never 140°, so there's just no answer.
I know I'm really bad with being consistent with colors, but I do try.
What about the range of inverse tangent? I guess it's like written right above, but I still want you to say it.
Negative pi over 2 to pi over 2, excluding this time.
Domain of inverse tangent. Yeah.
So is that can we use our unit circle
Uh-huh.
on top of like how we should have with it?
Uh,
Or do you want us to draw all the sheet?
I think here is the most useful thing you can do. So the unit circle that I gave you on that piece of paper is like the whole sheet of paper. I still only want to allow you one piece of paper. And I'm going to do my standard thing where you don't make that sheet back. So I think it would be most useful for you to draw a much smaller unit circle that's like not the whole sheet of paper. Because then you also have to like write down all the numbers, and that's like studying. So yeah. And like, these seem like a reasonably useful picture. I see what you want to remember. Cool. All right. So that's all from like the unit circle point of view. There's also a right triangle point of view on all of these things. Let's try to use the philosophy of right triangles to think about these. I'm not going to ask you like what they are, but I'm going to draw a picture of them. And
see what we can say using that. So let's call this angle theta. The inverse sine of 6/7, let's just call that theta. So it's an angle that's in the range of inverse sine. So it's got to be in quadrant 4 or quadrant 1, it looks like.
But it also has to be the inverse sine of 6/7. So here's an easy question. If theta is the inverse sine of 6/7, then what is the sine of theta? Yeah, just say it louder. 6/7. If I tell you theta is the inverse sine of something, that means I'm telling you this is an angle which has that as its sine.
Let's draw a picture of that. So if I tell you this is an angle in quadrant 1, that's important, whose sine is 6/7, what sides of this right triangle could you label? Yeah.
Opposite and hypotenuse.
Opposite and hypotenuse. How should they be labeled?
That would be 6, and the hypotenuse is 7.
Cool.
So there's a thing you can do. You can draw a right triangle that tells you things about inverse trig functions. There's one. Let's see an example where like something complicated is going to happen. Let's try to draw a picture for the inverse tangent of the natural log of 0.235. And let's start with this question about that. That thing inside of the parentheses.
This natural log of 0.235 that I've underlined in purple.
Is it positive or negative? And before you take out the calculator, let's like try to reason our way through. Let's suppose that this was an all or none multiple choice question where you're not ladder machining. Is the ln of 0.235 positive or negative? Negative. Why negative?
Because you turn it into exponential, it would be to something.
So if you want to know what the ln of 0.235 is, then you are asking and he gives like 2.7, so let's make things explicit all that, slightly wrong. What type of power do you need to raise 2.7 to get less than 1? Something negative. So this thing has to be negative. How many people have like what the graph of ln looks like in their head? No, I find that disappointing. I feel like you shouldn't. Graph logarithm functions or something like that, where this point here is 1, 0. So 0.235 is like there-ish, the y values. All right, okay, but
All that aside, this thing is negative. In fact, by using a machine now,
what is it negative approximately?
somewhere around negative 1.4. So if I want to think about this, I want to think about the inverse tangent of about negative 1.4. So let's think about it in terms of range of inverse tangent. This is an output of inverse tangent, so it has to be in the range of inverse tangent. That means it will be in either quadrant 1 or quadrant 4. So between quadrant 1 and quadrant 4, those are the only options you're allowed. Where is tangent negative? Quadrant 4. So this angle is in quadrant 4 and has tangent equal to negative 1.4. Let's draw a picture of it. So now you know the tangent of this angle is negative 1.4. According to SOHCAHTOA, what sides of this triangle might you be able to label? Opposite and adjacent. How would you like them labeled? If I want to write negative 1.4 as negative 1.4 over 1, is there a more canonical choice now? Yeah, it's not the only choice, right? It could be negative 14 over 10. If you like whole numbers, then do that. So it's 1.4 down and 1 across. There's a philosophy you can use to think about inverse trig functions. You can draw a triangle that tells you things about it. So with that in mind, let's go to the idea of the formulas that I want to get today. I want to study things like trig function evaluated at inverse trig function. So things like, I don't know, tangent of inverse sine of x. So let's get formulas for things like that. The only things that I'll get formulas for today are for things like sine of inverse cosine and cosine of inverse sine, but the ideas that we'll get will apply across other examples. And in order to think this through, let's start with 3 easy questions. What is the sine of the inverse sine of x equal to? X. Is that true for absolutely every value of x? You're kind of right. But can you plug absolutely every number into inverse sine? So it's not true when inverse sine doesn't exist. Sine of the inverse sine of x is always equal to x, as long as you're in the right domain. What's the domain of inverse sine? Negative 1 to 1. What about the cosine of the inverse cosine of x? Also x? Right, the way to think about that is inverse cosine of x is an angle whose cosine is x. If I give you an angle whose cosine is x and ask you what is the cosine of this angle whose cosine is x, then you would just say, well, you just told me the cosine is x. So it's x. With the same domain constraint. Inverse tangent of the tangent of x, also equal to x. But what's the domain of inverse tangent? So there is no constraint on the domain. All right, let's use these ideas to get those 2 formulas. I thought I didn't have enough time to get both of those formulas. Before we get a formula at all, let's try to do a single computation which will have all the ideas we need. If you internalize these ideas, then you can do everything involving this sort of technique. You won't really need the formula. Let's try to compute the inverse of the inverse sine of 3 over 5. So here's the game I'll play. You should think of the inverse sine of 3 over 5 as being an angle. Inverse sine of 3 over 5 is an angle. And what is the sine of that angle? Negative 3 over 5. Yeah, that's what inverse trig functions mean. And in fact, let's go to a unit circle picture and tell me, what quadrant is this angle in? And let's just ask. So a show of hands for each quadrant. The options will be yes, no, and maybe. Quadrant 1, yes. Quadrant 1, definitely no. Quadrant 1, maybe.
So let's, those of you who said definitely no, why definitely no? Yeah, the sign is negative. In quadrant 1, sign is positive. Quadrant 2, definitely yes, definitely no, or maybe. Definitely no. Definitely yes. Maybe or unclear. All right, let's think it through. In quadrant 2, I did say quadrant 2, right? In quadrant 2, are the y values positive or negative?
Positive.
Positive. Do I want a y value that's positive or a y value that's negative? Can't be quadrant 2. Quadrant 3. Oh, God damn it, Chris. You're off screen. I mean, you missed me drawing X's in those quadrants. So. Didn't lose one. Quadrant 3. Definitely yes, definitely no, maybe. Quadrant 3. Definitely yes. Definitely no. Maybe. All right. So I saw one hand for definitely no. Why definitely no? Yeah. Because the x value is negative.
And so is the y.
But I want sign, not negative. But your conclusion is right. It is not in quadrant 3. And to do that, let's remind ourselves, what's the range of inverse sign? That's the domain. Negative pi over 2 pi over 2. So now I'll ask you again, could this angle possibly be in quadrant 3? Nope, it's not, because it's an angle that's between negative pi over 2 and pi over 2. So what quadrant is this angle in? Quadrant 4. So I'm going to draw an angle in quadrant 4 whose sine is negative 3 over 5. And there's like a picture of this angle with a happy little right triangle sitting here. And let's go ahead and answer this question first. This is an angle that's in quadrant 4. Will cosine be positive or negative? Positive. So we know at least that much. It'll be positive. And let's figure out what positive number it is. And let's use this triangle to do this. So this angle has a sine of negative 3 over 5. What sides of that triangle could I label? Yeah. Opposite and hypotenuse. How would you like them labeled? Cool. How many people don't like that the opposite is labeled with a negative, though it's a sideline? That's fine, you can dislike that. In this case, like, the negative does mean something, like it's pointing down. So I'm going to leave the negative in because it does actually mean something here. But it won't actually affect our analysis anyway. Is this enough information that we could find the length adjacent? If we knew the length adjacent, could we compute cosine? Cool, let's compute the length adjacent. And maybe I'll leave this like 2 options. Should I do the work to compute the side length adjacent? All right, let's do it. What's the important equation that you need to remember if you want to like find one side length given 2 other side lengths on a right triangle? A squared plus b squared equals c squared, the Pythagorean theorem. So, let's see, by Pythagoras, let's call this ADJ for adjacent. Adjacent squared plus negative 3 squared, or just 3 squared, depending on how you've labeled the triangle, equals 5 squared. Does that look easy to solve for addition? I bet so. Right, 5 squared is 25. Negative 3 squared, or just 3 squared, depending on how you labeled it, is 9. So subtract that 9 to the other side. Still squared, though. So adjacent squared is 16, so how long is the adjacent side length?
I like that. Let's stick the plus or minus in and decide whether we want plus or minus. Plus or minus? Plus. Yeah, I'm going to the positive direction. All right, so this picture is getting messy, so let's relabel it. 4, -3, 5. There's this angle that I want to understand. Could I use that triangle to compute cosine of theta? Nice. What's the cosine of theta?
30.
Notice I didn't ask you what the angle theta is. I want the cosine of theta. 4/5. Cosine is adjacent over hypotenuse. And in terms of saying what this angle numerically is equal to, this turns out to be an angle that you can't really compute on the nose, at least not using the techniques we have.
Sine inverse. So let's just make one quick reminder that you can use machines for a bunch of these things. According to your calculator, what is the inverse sine of -3/5? I see it at -0.6-ish radians. Or -36.9-ish degrees. Folks feel all right? Nice. So, do you think using these exact same ideas you could do this for basically any input? Let's do it once for a general input with a variable x, and then we'll write down a few conclusions. So, let's try to get a formula for the cosine of the inverse sine of x. We'll see what we get. So here's the game we'll play. You look upset about something.
I'm just going to see what the answer was.
Oh. Cosine of sine inverse of 3/5 is 4/5. Because we wanted the cosine of this angle. Cool. So, let's now try to do this in more generality. Basically, I'm just going to replace this -3/5 with a variable. So let's replace it with x. So let's let theta be, let's compute the cosine of the inverse sine of x. To do that, well, inverse sine of a thing is an angle. So I should think of inverse sine of x as being an angle. I will call it theta. If theta is the inverse sine of x, then what is the sine of theta? X. If I tell you theta is the inverse sine of x, I'm telling you theta is the simplest angle with sine equal to x. So in particular, its sine is x. So let's draw a picture of that. So if I give you an angle whose sine is x, then what sides of that triangle could you label? Opposite and hypotenuse. What should the opposite be? Hypotenuse? 1. Because you could write that as x divided by 1. You could have written it in a sillier way, like x squared over x. But I think that would needlessly complicate everything. Nothing terrible would be a consequence, but it would make it easier to assume something else. Could you use that to find the length adjacent? I bet. Let's try to find the length adjacent. I'll call it ADJ for adjacent. And it's the same equation we need to solve. X squared plus adjacent squared equals 1 squared. Solve for the side length adjacent. That look easy to do? Like maybe we can't do it in the 30 seconds I have remaining. You'll get plus or minus the square root of 1 minus x squared. Should it be plus or should it be minus? Plus. One way of seeing that is in the range of inverse sine, is cosine positive or negative? Positive. So you get a general formula for the cosine of the inverse sine is the square root of 1 minus x squared. So, I think the thing that we will start with next time is some very similar examples, but with like what trig function is inside and outside switched over. So if you want to make the start of the next lecture really pleasant for you, just like go through the rest of the section. It doesn't involve any new ideas on top of what we've already done, and you can check your answers using the machine.
So on like a text or something, would allow like a circle or the right triangle method? Okay. I was like trying to use the Buster method. Like the right triangle that makes a difference.
The unit circle is helpful to see like, should the answer be positive on it?
Yeah.
Because sometimes that's all it looks like. Oh, thanks for bringing it back. Yes. Okay. Okay. Yeah, that's always useful. Let me know. So I think send me an email with all this because otherwise I'll be distracted. Stay on the email.
Okay.
When do you think you'll be back and where to stay?
Probably that like Monday or Tuesday or whenever it's possible, like after next week.
Okay, cool. Include that in the email because I'm terrible about this.
Okay, sounds
And I guess you'll be missing like the review day for the sixth.
Probably, yeah, if it's next week.
So, like, do you feel comfortable enough with the material right now that you feel like you can just take leave it?
Probably not.
Okay. Well, yeah, we'll do it like after you get back.
Okay.
But go through this.
Yeah, I have that.
Decide if you want to like add an extra day of hedging so you can discuss
Okay.
stuff.